Hi everybody, welcome to Phys 3500 Classical Mechanics. I'm your instructor, Dr. TJ Hammond. Today we'll be reviewing oscillations in two dimensions and how we can make these into parametric equations. On Monday we talked about harmonic oscillations in one dimensions, and we reviewed simple harmonic motion and how we can use that for, say, a pendulum swinging or a physical pendulum, or approximations for anything that's near equilibrium position. In this lecture, we're going to be expanding on that. So instead of being in one dimension, we're going to talk about this in two dimensions. The reason why we're going to be talking about this in two dimensions is because there are many examples of when we can't just simplify this in one dimension, and we'll be dealing with a lot of these cases actually in this course. So when we get to gravity, so we'll be talking about this a little bit on Friday, and then later on in the semester, when we're dealing with planetary motion and central forces, we'll be talking about motion in two dimensions there. Also, when something scatters, that will also be obviously two dimensions. But even waves, so towards the end of the course, when we have something oscillating, we have this wave motion in one direction, but this wave propagates in the orthogonal direction. And especially when we get to Chapter 10, non-inertial reference frames, we'll definitely be dealing with cases where motion isn't in just one dimension. And then for your final project, you'll also be dealing with rotational motion, and rotational motion is, of course, in three dimensions. So before we get there, we're going to start off in the more simple case of just two dimensions. For the daily assignment, read Chapter 3.3, Harmonic Oscillations in Two Dimensions, and upload that by Friday's tutorial. If you're taking statistical mechanics in the winter, I'd also recommend reading section 3.4. It's only a few pages long. It's just kind of to get a bit of a jump on phase diagrams, and what phase diagrams are is, instead of having motion in two dimensions, it still can be one motion in one dimension, but it's that you have x in one axis and x dot in the other axis, and then you basically parametrize the motion in these two dimensions. All right. So looking at harmonic oscillations in two dimensions, now this particle can move and it has 2 degrees of freedom. So that means that this force is now still proportional to the spring constant, negative k, and then still proportional to this distance, but r can take on any direction, right? So we can even change our axes. So for the assignment the other day, we also looked at what happens if we rotate our coordinate system, phi prime, where this has, say, an angle theta, and then this would have an angle, say, zeta. We can rotate our coordinate system so that this can be described, in any rotated frame. So this isn't necessarily unique, but we're just going to stick with the frame that we have here. Okay, so of course, using Newton's second law, we break this down into constituent components. So f of x is equal to negative kr cosine theta, and that's going to be negative k in the x direction. And fy is equal to negative kr sine theta, or that's negative k times the y amplitude. So in this case, of course, k is the same for the x direction as well as for the y direction. That's not going to be generally true, but for the simplest case, we'll assume that it's true. But there is an example when this is the case, and that's a pendulum. So say if you were to have some mass tied to a string, so say this is a top view, and we pull it to some amplitude a at the beginning, and then we let this thing go, this thing is going to swing back and forth in x, right? And so now, since we're going to talk about motion in two dimensions, this would of course be y. But that's not a unique axis. We could even have rotated frame. So this would be x prime, and this would be y prime, and this could be your angle theta. And so in that case, instead of being motion in 1 dimension, it's now motion in 2 dimensions. Okay, so let's talk about this. So as I said, we've broken this down to its constituent components. So now we have 2 second-order ODEs. So we get x double dot plus omega naught squared x is equal to 0, and y double dot omega naught squared y is equal to 0, where omega naught squared is going to be k over m for a spring, or as we derived last class, omega naught squared to be g over l if it's a pendulum with small amplitude. The solutions for this are going to be x of t is equal to a cos omega naught t minus theta in the original phase in the x direction, so that's theta x naught, and yt is equal to b cos omega naught t minus theta y naught. So this form where we have this cosine of omega naught t minus theta minus its phase, we already knew that from last class, and as we said, when we have this arbitrary a and this arbitrary phase, we can have this as our solution to a second order homogeneous differential equation because that's the simplest case. Okay, so this still satisfies the same conditions that we had before, that we need to have 2 orthogonal solutions for a second order differential equation. It just happens that we've written in a more compact notation effectively. But the frequency is going to be the same. So obviously we have omega naught in both of these, and they're the same omega naught, and that's because we have the same spring constant for both, or say the same pendulum length for both directions. But the motion in the 2 dimensions can actually differ based on what that amplitude A or B are, or what that initial phase is, theta and theta x naught and theta y naught. Okay, so we want to parametrize these equations, and what that means is that right now we have these equations written as x of t and y of t, and what we want to do is write this in terms of y of x, or we could write it as x of y. Either way is the same. We're parametrizing time, and we're making these functions depend on each other. Okay, so I've written out the math here for this. It's a little, it's not particularly complicated. It just takes a little bit of time. And so we still have this same equation here. This b y of t is equal to b cos omega naught t minus theta y, and we can put a little 0, but I'm going to be dropping that 0 notation for this. Oh, I guess I should have it here too, but I'm just going to drop it for the rest. And then we also have, but the thing is that we can also add theta x naught and subtract theta x naught, and so that doesn't change the function at all. But that does allow us to rearrange terms, and we can also define delta as the difference between our initial conditions in x, or initial phase in x, and our initial phase in y. And so that's b, so that allows us to write it as b cos omega naught t minus theta times cos delta, right? Because we get this plus here, and then we get this minus here, minus b sine omega naught t minus theta x sine delta by the triggered entity. But if you think about what this cosine omega t minus theta is, that's exactly what this term is here. And we have a sine, this sine term here. But if you remember from triggered entities, cos squared alpha plus sine squared alpha is equal to 1, or sine squared alpha is equal to 1 minus cosine squared alpha, or sine squared, or sine alpha, sorry, is the square root of 1 minus cos squared alpha. Okay? And since we just said that this cosine term is x over a, well then what we get is that sine is going to be the square root of 1 minus x squared over a squared. Okay, and we can substitute in those expressions, and we get that the first term is b over a times x cos delta. The second term is b times the square root of 1 minus x squared over a squared times sine delta. All right, and then we can just expand that out. And so what that gives us is ay is equal to bx cos delta minus b times the square root of a squared minus x squared times sine delta. But what that, it's much simpler if you have square roots. If you're trying to solve for these equations, you try and put all the square root terms on one side, or you try and put the square root term on one side and all the non-square root terms on the other side, and then that way, when we square these, you get rid of that square root term. So square both sides, and what you get is a squared y squared minus 2abxy cos delta plus b squared x squared cos delta squared is equal to b squared a squared minus x squared times sine squared. But there's going to be a b squared x squared for sine squared delta and for cosine squared delta, and so you put those two things together, and of course, as we just had in the previous slide, cosine squared delta plus sine squared delta is equal to 1. And so we can simplify this, and we get this parametric equation. A squared y squared plus b squared x squared minus 2abxy cos delta is equal to a squared b squared sine squared delta. Now, in this case, of course, x is still dependent on t, y is still dependent on t, but t isn't explicitly showing up in this equation. So we've parametrized this, right? So we now have x as a function of y, or y as a function of x. So this is still fairly complicated. You probably don't have a great intuition for what this means yet. So we're going to look at some specific cases. Okay, so if we look at specific case for delta is equal to 0. So if we have delta is equal to 0, then that gives us 1. And sine squared, if delta is equal to 0, then this is going to be equal to 0. So then what's left over is you can simplify this to get y is equal to b over a times x. So now what this means is we've had this mass at some point. We've pulled it to some distance, where this distance r is equal to, say, a, or sorry, this is negative a, and this distance is negative a, and r is a times root 2, of course. You've pulled it out to here, and then you let it go. And so this mass on a simple harmonic motion would go to here, and then oscillate back and forth and back and forth. And so this black line is tracing out that path. So for all time, basically. Okay, we can also say that delta is equal to plus or minus pi. So in the case plus or minus pi, then this is going to be negative 1, and sine pi is still going to be 0. And so instead what we get is y is equal to negative b over a times x. And so again, we do the same thing, that we pull this out to some initial position, and then we let this thing go, and it'll oscillate back and forth along this line. So that would be viewing a pendulum from above. We can also have this going in more interesting shapes. So if we take delta is equal to plus or minus pi by 2, then what we get for the equation is a squared y squared plus b squared x squared is equal to a squared b squared, or you divide by a squared b squared and you get y squared over b squared plus x squared over a squared is equal to 1. And what's that equation of? Well, you can see what these objects look like. So if a is equal to b, then what you get is this amplitude and this amplitude are going to be the same. And so what happens is that you're releasing this thing, and it's following this trajectory here. And that is, of course, a circle going in the clockwise direction. And in this case, in the second case, if A is equal to B by 2 and delta is equal to negative theta by 2, then this object goes around in this direction, and it follows, instead of being a circle, it's now an ellipse, which is just a general circle. Okay, so if you actually create a little animation that does this, and so we go from time t equals 0, and you can see that this thing follows those circles of those ellipses. Okay, so something more interesting is in the general case, what if the spring constants aren't equal? So instead of this being, say, a pendulum or two identical springs, these springs are slightly different. So now you have different amplitudes where A is equal to B by 2, and omega x is 3 omega y. And then if we release this thing, well, this thing is going to oscillate back and forth, but it's going to oscillate in the x direction at a different frequency from the y direction. So for every one oscillation in the y direction, it's going to oscillate 3 times in the x direction. Okay. And then on the right here, we see what happens if you have the two frequencies are just ever so slightly different, that this thing oscillates back and forth, and it takes a really, really long time before it actually repeats upon itself. And so these are called Lucid curves. And so we can have a little animation of that. So on the left, you see when they're different a factor of 3, that it starts at this point here and oscillates. And so for one oscillation in y, where it goes up and down once, it goes 3 times in x. Okay. Now on the right-hand side, the difference isn't that great, or they're not quite like simple fractions of each other. So it's 3.1 times different in harmonic frequency, or in the fundamental frequency. And so you see that it doesn't quite repeat back on itself after one oscillation. And so then you actually have to think about this for a lot longer before it actually fully repeats back onto itself. And so, but eventually it will. In the case where omega y, say if omega y were equal to, or sorry, omega x were equal to pi omega y, then in that case, this will never actually repeat on itself because it's an irrational number. Same thing as if you had like omega x equal to √2 omega y. Then because it's an irrational number, these things will never return back to the original position. All right, and that's all I wanted to talk about for this. So I will see you in class.